Okay, so let's picture this. A form of matter, incredibly strange, really tiny, but so powerful it could punch holes clean through materials.
Right. And not just that, but transmute elements fundamentally challenge how we think about physics.
Exactly. We're talking about something often called microball lightning. Now, this deep dive is definitely for you, whether you're a scientist perhaps exploring these new frontiers, or maybe an energy executive looking for that next big breakthrough.
Our mission today, really, is to distill this fascinating, sometimes, controversial world of exotic vacuum objects, or EVOs.
And really unpack their incredible potential.
Yeah, and what's truly compelling, I think, is that EVOs aren't just some theoretical flight of fancy. The sources we're looking at reveal pretty robust experimental observations. They're hinting at a completely new framework, potentially, for energy and material science.
So what are we digging into specifically?
Well, we'll look at how these enigmatic objects are actually created, how they're sustained in the lab,
Okay.
the really extraordinary elements they seem capable of producing.
That sounds wild.
It is.
Yeah.
And then there's this tantalizing prospect of actually controlling them, using technologies like electromagnetics, maybe lasers.
Which, if possible, could revolutionize pretty much everything, couldn't it? Manufacturing, clean energy.
That's the potential, yes. A huge shift.
All right, let's start with the basics then. What exactly are these exotic vacuum objects, these EVOs?
Okay, so the sources describe them as highly organized, micron-sized clusters of electrons.
Micron size, so really small.
Tiny. Think maybe 5 to 15 micrometers across. But, and this is the kicker, they're packed with an immense number of electrons.
How many are we talking?
Over 100 billion, easily. Some researchers even throw around numbers like Avogadro's number, though that's more speculative.
Oh. And they get called different things, right? Electron clusters?
Electron cluster, or charge clusters, yeah. And significantly, microball lightning, because their behavior really resembles it sometimes.
Okay, and you mentioned behavior. What's key there?
A critical characteristic is what's called soliton behavior.
Soliton, like a wave that doesn't break.
Exactly like that. Imagine a perfect wave, just traveling along, never losing its shape, never dispersing. These EVOs seem to do that. They maintain their integrity.
Against forces that should rip them apart.
Precisely. Which is the huge theoretical challenge here. You see, the very existence, the stability of such a dense clump of electrons, it just completely defies classical electrodynamics.
Because of Coulombic repulsion, right? Like charges should repel violently.
Absolutely. They should just fly apart instantly. There's actually a great story in the sources about Richard Feynman.
The Nobel laureate.
That's the one. He initially dismissed the whole idea as, quote, nuts.
Can't blame him, based on standard physics.
But later, faced with the evidence, he apparently had to concede its correctness, which is huge.
That's incredible. Empirical observation forcing a rethink of fundamental theory.
It really highlights the challenge. It suggests there must be some previously unrecognized cohesive forces at work, or maybe a totally novel energetic state.
So they're not just random clusters.
No, not at all. They're described as coherent structures. Some even speculate they could be macroscopic quantum states or coherence-bound solitons. It points towards some kind of self-organizing principle we just don't fully understand yet.
And the effects they have are pretty dramatic, too.
Oh, definitely. They can cause these microscopic holes in materials, as you mentioned.
Yeah.
They can also induce something called a low-energy phase transformation.
What does that mean in practice?
Imagine solid metal turning liquid, but without obvious signs of heating, like ice melting, but without the temperature rise you'd expect.
Weird. Almost like it's changing state differently.
Something like that. And they're linked to incredibly high temperatures in things like sonoluminescence cavitation bubbles collapsing, up to 20,000 Kelvin.
20,000? That's hotter than the surface of the sun.
Indeed. And maybe the most radical idea, some theories suggest they might tap into the quantum vacuum itself. Zero-point energy.
Drawing energy from empty space.
That's the concept. Ken Shoulders even coined a term for it. Potentum.
Yeah.
It's very out there, but it's part of the theoretical landscape.
So, okay. These tiny electron clusters defy repulsion, liquefy metals without heat, maybe tap vacuum energy. What does this mean for, the people listening, the scientists, the executives?
Well, for the scientists, it's a whole new playground, isn't it? New forces, new states of matter.
They're the energy executives.
It could represent a complete revolution in how we think about generating and using energy, if any of this can be harnessed.
Right. It forces us to really reevaluate some core physics principles.
Especially in condensed matter and plasma dynamics. It's not just a little anomaly, it could have huge implications.
Okay, so we know roughly what they are and why they're so puzzling. The next big question, especially for anyone thinking about practical applications or, frankly, funding, how do you make them? And maybe more importantly, how do you keep them stable?
That's crucial, isn't it? And the sources show a surprising variety of methods people have used.
Like who?
Ken Shoulders was a real pioneer here. He talked about creating baby ones and then, quote, growing them by feeding them more electrons.
Feeding electrons. How?
He often used a penning trap, which is basically a clever configuration of electric and magnetic fields.
Like a magnetic bottle.
Sort of, yeah. It traps the electrons and allows you to accumulate them, essentially feeding the EVO structure.
So electromagnetics are involved right from the start in controlling them.
Absolutely. But he also used simpler methods. High voltage pulses onto an insulator over a metal ground plane, even just basic cathode-anode setups.
And could he make them last? What about sustainability?
Shoulders seem to believe they could stay in metals indefinitely if the conditions were right, and if they were continuously fed.
But otherwise they just fade.
Yeah, he said they'd fade away and disappear if not attended to, which makes sense for a high-energy state.
But here's something I found amazing in the notes. Reactivation.
Oh, yes. That's a remarkable finding. One researcher apparently took EVOs that were dormant in copper oxide for 9 months.
9 months. And then what?
Just by heating them slightly, or even exposing them to sunlight, they were reactivated. They came back.
That level of persistence is just extraordinary. It doesn't sound like typical plasma behavior.
Not at all. It suggests something much more stable, maybe interacting with the material substrate in a deep way.
Mm-hmm.
And it's not the only way to make them. Cavitation's another big one.
Right, collapsing bubbles in liquid.
Exactly.
Yeah.
Alexander Shishkin used things like a hydrosonic pump or spinning cones to create intense cavitation. And this process emitted what he called strange radiation.
Which he identified as EVOs.
Correct. But he had this really peculiar problem.
What was that?
His device would work for a while, producing EVOs, and then just stop.
Equipment failure.
No, because all he had to do was physically move the entire setup to a different spot in his lab, and it would start working again.
Move it. That's bizarre. What could that possibly mean?
It's led to some pretty wild speculation. Could the EVOs be using up some kind of localized environmental factor?
Like what?
Some theories mention things like a relic neutrino flux, or even tapping into the ether, though that's highly controversial, obviously. But it suggests some kind of environmental interaction might be needed to sustain them long term.
Fascinating. So it's not just about the device, but maybe the location too.
Potentially. Others, like Roger Stringham and Tom Claytor, used ultrasonic transducers. Pretty standard lab gear, from 24 kilohertz up to 1.7 megahertz.
And didn't they mention a really simple setup?
Oh yeah, apparently a 3-year-old experiment just used a regular domestic ultrasonic cleaner, the kind for jewelry.
Seriously, like 43 kilohertz?
Around that, yeah, with just water and some aluminum foil. And they reportedly produced EVOs.
It's just amazing the range of methods. High-tech penning traps, spinning water, household cleaners. And you mentioned they pop up elsewhere too.
Yes, incidentally. They apparently invariably occur in things like the Farnsworth fusor, an early fusion concept.
And they're a nuisance in modern fusion research.
A significant problem for tokamaks, yes. They're linked to things called diocotron instabilities and magnetic islands. Basically plasma turbulence that can mess up the confinement and even damage the reactor walls.
So they're appearing naturally, or at least incidentally, in these high-energy plasma environments.
Which tells you they're a real physical phenomenon, not just some lab artifact from one specific setup. We also see similar structures forming from electrical discharges.
Like lightning.
On a smaller scale, yeah. Winston Bostick observed electrical discharges forming these loops of flux that would reconnect into stable torus shapes, like donuts, plasmoids.
Self-organizing plasma.
Exactly. He even saw tori of tori, hierarchical structures, and other experiments using like 700-volt discharges near brass plates produce these tiny, iron-rich crenellated microspheres.
Which are considered what?
Indicators of ball lightning structures or related phenomena. So again, linking back to that microball lightning idea.
Okay, so the ability to make them in diverse ways, sustain them, even reactivate them, it really points to something robust.
It does. And the challenge now, the real opportunity for, the scientists and engineers listening is moving beyond just making them incidentally or in specific setup.
To controlling them, making them predictably.
Precisely. Controlled, predictable generation and maintenance, especially given what they might do.
Which brings us to the next, maybe most startling part, what these things can apparently create. We're talking elemental transmutation.
Yes. This is probably the most revolutionary and controversial claim associated with EVOs.
Where did this observation come from initially?
Again, Ken Shoulders reported critical observations. When he impacted EVOs onto metal oxide surfaces, things like aluminum oxide, he detected new elements in the impact crater and the ejected melted material.
New elements, like alchemy?
Well, low-energy nuclear reactions, or LER is the more common term now. But yes, elements that weren't there before. And crucially, this effect was not seen when he used highly purified metal targets, only on the oxides or perhaps other complex surfaces.
That specificity is interesting. It suggests the surface material plays a key role.
It seems to, and it directly connects EVOs to those persistent, often debated claims about LNR or cold fusion.
But it gets even more extreme with cavitation, right?
Mark Leclerc's nanospire experiments.
Yeah.
Yes. He was spinning water in a PVC tube with a piece of perforated aluminum inside.
And the claim was?
Astonishing, frankly. He reported producing potentially all elements in the periodic table.
All elements. That seems biologically impossible, almost.
It's a hugely controversial claim, let's be clear. But that was the report, accompanied by strange radiation tracks. He theorized it was like small-scale supernova nucleosynthesis happening inside the collapsing bubbles.
Like tiny star explosions creating elements.
That was his interpretation. And significantly, he also reported excess heat generation.
Energy out greater than energy in.
Yeah. The coefficient of performance, or COP, of 3.4. He claimed 2,900 watts of hot water output from only 840 watts of electrical input.
If true, that's massive. Free energy plus new elements.
It would be paradigm shifting, absolutely. Stringham and Claytor also used their ultrasonic setups, specifically aiming for element transmutation as well.
So, stepping back, the potential here is immense. If you could reliably trigger these transmutations.
Think about it. Cold machining of materials at the atomic level, synthesizing specific, maybe rare elements or isotopes on demand.
Neutralizing nuclear waste, perhaps. Turning dangerous isotopes into stable ones.
Well, that's one of the hopes, yes.
Yeah.
Without needing giant accelerators or reactors, without the intense heat and radiation, it's a potential game changer for manufacturing, materials engineering, waste management.
And for energy production, if the excess heat claims hold up.
Exactly. For you, the energy executive, imagine clean energy generation coupled with valuable material production. For you, the scientist, it fundamentally challenges nuclear physics as we know it.
It moves from just being a weird physics curiosity
To something with potentially enormous, tangible applications for society. A low-energy pathway to nucleosynthesis and clean power.
Okay, so creation, sustenance, transmutation. The final piece of the puzzle, and maybe the most critical for realizing any of this potential, is control.
Right. How do we move from observing these effects to directing them?
And the sources suggest electromagnetics and lasers might be the key.
They seem to be the most promising avenues explored so far. Remember the pinning trap Shoulders used?
Yeah, the magnetic bottle thing.
It inherently uses electrical and magnetic fields. For confinement, yes, but also for feeding the EVOs. So influencing them with EM fields is baked in from the start.
And there are theories about why magnetic fields might be so important.
Yes, some models propose that the stability of EVOs, especially if they have that toroidal donut shape, might come from the rapid motion of the electrons themselves, generating intense internal magnetic fields strong enough to counteract the electrostatic repulsion.
So the magnetic field isn't just containing them, it might be part of what holds them together.
Potentially, yes, which strongly suggests that external magnetic fields could be used to manipulate them, to guide them, maybe even stabilize or destabilize them.
And there were other magnetic links mentioned.
Observations during cavitation of metals in water also noted the creation of magnetic charges, or monopolies, though that's another area of physics debate. But it further ties EVOs to magnetic phenomena.
It paints a picture where magnetic fields are deeply intertwined with these objects.
A very strong interplay, yes, which suggests a powerful lever for control if we can figure out how to use it precisely.
Okay, what about lasers? That sounds even more high-tech.
Well, some cutting-edge simulations, relativistic laser plasma simulations done by international labs, they've actually shown the generation of structures under intense laser conditions that visually resemble the observed EVOs, complete with incredibly strong magnetic fields up to 1,000 Tesla.
1,000 Tesla, that's astronomical.
It's huge. And it shows that powerful lasers can definitely create the kind of extreme environments where EVOs might form.
Is there a theory for how lasers might create them directly?
Yes, some theories propose that lasers could essentially concentrate photons with such intensity that they create matter, potentially miniature black holes or perhaps EVOs,
Yeah.
acting like tiny particle accelerators.
Wow. So lasers could be both a creation tool and potentially a control tool.
That's the implication. Now, connect this back to the transmutation.
Okay.
If high-intensity lasers can create EVOs, perhaps very precisely,
Mm-hmm.
and if EVOs are proven to cause elemental transmutation.
You could potentially use lasers, maybe guided by magnetic fields, to create specific elements on demand.
Exactly. The ability to precisely control the creation of EVOs, their properties, their impact location, using lasers and electromagnetics, that opens a pathway to potentially controlling the types and quantities of elements produced.
That's the holy grail, isn't it? Directed material synthesis at the nuclear level.
It represents a huge potential leap, moving beyond just observing transmutation to actually engineering it.
So imagine that capability. Precisely targeting these micro ball lightning structures, maybe conjuring them with lasers, steering them with magnetic fields. The idea of controlling element production. That's where the real excitement must lie for researchers and funders.
Absolutely. When you look at the big picture, the convergence of these tools, powerful magnetic fields, concentrated laser energy with the phenomenon of EVOs and their transmutations, it offers a really compelling vision,
Not just making them, but guiding them.
intentionally guiding their behavior to engineer matter, right down at the fundamental level. If that becomes feasible, it truly changes the game for materials, for energy, for resource management.
Okay, let's try to wrap this up. We've taken quite a deep dive today into exotic vacuum objects.
We certainly have. A phenomenon that really pushes the boundaries of our physics understanding.
We went from Ken Shoulder's early work actually sustaining these microball lightning structures in his lab.
Right. Through to those, frankly, astonishing claims about creating potentially all the elements in the periodic table using cavitation. The implications are just vast.
And that raises a critical question, doesn't it? As we get better at understanding and maybe controlling EVOs, using these precision tools like electromagnetics, high-power lasers, what does that unlock?
What new possibilities emerge? For energy generation, sure, but also material science, maybe even dealing with things like nuclear waste.
And the fact that these things show up incidentally in fusion devices.
It really signals this isn't just some, fringe science. It seems to be a fundamental aspect of high energy density physics that we need to understand. It could be critical for future breakthroughs.
So for you listening, the scientists, the energy executives, anyone considering this frontier, what if mastering these strange, self-organizing electron clusters really is the key?
The key to unlocking entirely new forms of energy, completely new ways of manufacturing materials.
What new elements might we learn to create intentionally? And what could that mean for humanity's future, really, on this planet and maybe even beyond?
That's the provocative thought to leave you with. Where could this lead if we truly cracked it?